we're finishing section 6.5. We're learning how to write parametric equations. Okay, so what we're going to do is just an example. So the instructions for this example are write a pair of parametric equations that will produce the indicated graph. Now there's usually different ways to do these, and so your answers might be different than someone else's. So the way your book says that is answers may vary. Okay, we are going to do an example with a line segment that starts at 1, 3. At time equals 0, the x and y values where it begins is at 0.13 and ends at time equals 2. I don't know whether it's 2 hours, 2 seconds, 2 minutes. I don't know. It doesn't say. So that's just our time value. And it ends up ending at the 0.58. So the idea behind parametric equations is that the parametric equations graph an object in motion. So the path of an object in motion. So not only do we have x and y that tells us the position of the object, but we also have time t that indicates the time that it's at that position. Okay? So when you have parametric equations, instead of having one equation you have x and you plug in x to find y, you usually have two equations where you plug in t to find x into one equation and you plug in t to find y in the other equation, right? So that's what we're trying to do here. So we have x, y, and t. Probably the best way to organize our information is to just put it into a table so we can see it all together, but we don't have to do that. It's just a suggestion. You might want to create a table. So in our table we have t, we have x, we have y. So these are the points I just gave you. At time equals 0, the starting point of the object in motion is 1, 3, and at time equals 2, the ending position of the object is at 5, 8. So if we just wanted to create an xy graph for this segment, these would be our x and y values. We would use these points to do an equation in the form y equals mx plus b, right? Which means we would have to find the slope and we would have to find the y-intercept using those points. But we're not just finding an xy graph, we're actually finding graphs for x and y in terms of t. So it's the same idea, except that we're going to find one graph using t and x, one equation using t and x, and we're going to do the other equation using t and y, where you plug in t, get out x, or plug in t, get out y. So we'll have two different equations. Okay, so we will have, so it follows the same pattern as y equals mx plus b, but it's using t instead. So like x equals mt plus b. So it's where we plug in the t value, we get out the x value. But do you understand how this is the same exact pattern as a y equals mx plus b type of situation, right? So we're using t as the x and x as the y. So how do we find slope m? We have 2 points. How can we find slope using those 2 points? Normally slope is found by doing y over y minus x over x, or divided by x minus x. So it's like the distance between the y values divided by the distance between the x values. But in this case, t is actually x and y is actually t. I mean, x is actually y. I'm lost. Can you tell? Okay, so instead of the y values, what are we putting on the top? The x's, because they're pretending to be our y's in this equation. And then instead of x's on the bottom, what's the input value? What's the domain number? T. Okay, so let's take the numbers we have here. So let's subtract our x's. So like 1 minus 5, and then subtract the t's, 0 minus 2. So 1 minus 5 is a negative 4, and 0 minus 2 is a negative 2. What's negative 4 divided by negative 2? 2. So that gives us x equals 2 times t plus the y-intercept, or starting point. Now the y-intercept is always where x equals 0. Well, in this case, t is our x. So it's where t equals 0. What's the starting point for x? What's the starting point for this equation? 1. So the y-intercept is 1, and that came from those two numbers right there. So there is one of our parametric equations. Now let's do the other one the same way. So it would be y equals mt plus b. So this time we ignore the x values and we do exactly the same thing using the y and the t. So you plug in t, get out y. So t is in for x and y is itself. So do the same process for me really fast. See if you can do that on your own. Find the slope, find the y-intercept, make an equation. Y values are 3 and 8. T values are 0 and 2. Gives us a slope of 5 halves, right? Is that what you guys got? And then the y-intercept is where t equals 0, but we're just looking at the y value. So it's 3. So the y equation in this case is 5 halves t plus starting point 3. So there's our set of parametric equations for this problem. Now, anytime you have a set of parametric equations, you always also have the parameter. So you would also in your answer have to include the parameter from 0 to 2, right? Because that's where time starts and ends for this moving object. So we've got our x equation, parametric equation, our y parametric equation, and the parameter t for this particular situation. Now that only works, this situation, this example only pertains to something that's a straight line segment, right? So there's other shapes you might deal with that it might involve trig. I'm not sure if they make you do any of those this direction or not. I don't have any examples written down, so that's a good sign. But if you end up finding any, you need help with them, we can just go over those on Wednesday. Okay, we're good on those? I have one more example, and then we're done, and you can just work on, well, we'll figure out what we're doing from there. Alright. So we've learned that we can graph things in x, y rectangular coordinates, and we've learned that we can graph things in r, theta, polar coordinates, and now we've learned about finding the path of an object in rectangular coordinates. Well, what about the path of an object in polar coordinates? Could that be done? Yeah. So what we're going to do right now is talk about converting polar form to parametric. So we're going to use some formulas we learned in section 6.4. So not new formulas, something you already need to learn and remember, so we're not really changing that. Those are the formulas we will use to create our parametric equations. Now notice how there's no t involved at all? That's because when you use polar equations for parametric, that theta becomes the parameter instead of t. So let's just write that down. Theta is the parameter instead of t. Alright, let's do one example. Change the polar equation r equals 1 minus cosine theta to parametric. Okay, so remember when we have parametric equations, we have what x equals and we have what y equals. And usually we have x in terms of t and we have y in terms of t. But this time it's going to be x in terms of theta and y in terms of theta. So we just want to get rid of r. Okay, so instead of r, we will have it simplified instead. Okay, so looking at these equations right here, x is equal to r cosine theta and y is equal to r sine theta. They just told us that r is equal to this thing, 1 minus cosine theta. We want to get x and y in terms of theta without the r. Can anyone see what we can substitute into what to accomplish that? So we can take the value that they just gave us for r and plug that into our formulas in place of r and get rid of r so that we have them as a set of parametric equations instead. So taking the x, instead of r cosine theta, it would be 1 minus cosine theta times cosine theta. Which I guess if you really wanted to distribute the cosine, you could. I didn't do that on my paper, so I'm not sure how important it is. Okay, and then for y, we would just plug the r in for that. The stuff in for that r. So 1 minus cosine theta times sine theta. And there's our parametric equations for an equation that was in polar form. That was easier than the last one. Yeah. Now I think there might be some questions on your homework that have to do with projectile motion. So I have it written down here, so just in case I don't want to forget or have you unprepared for those. So think about a projectile that's shot into the air, like, you know, a cannonball or something. And so the boost of it being shot into the air takes it up into the air, and the angle factors in, and the acceleration, the speed that it's going factors into it. But then it gets to a certain point where gravity's too much, right? Gravity starts pulling it down at the same angle and speed. So it ends up making a parabolic graph. Okay, projectiles are known for parabolic graphs, such as in the game Angry Birds, right? So there's certain formulas we can use for the motion of a projectile and its location horizontally and vertically at a specific time within that projectile process. Okay, so let me give you the equations you would use for projectile motion. And then we're done. I'm not even going to do an example with them. I'll let you play around with them, see what happens. So x equals v sub 0. Any idea what that would stand for? Velocity, starting velocity. Cosine theta t. Now I'm trying to figure out if it's cosine theta times t or if it's cosine theta times t. I think it's like that, which means we ought to put those parentheses in there, right? Or that would be messed up. Almost positive. Okay, so v sub 0 is initial velocity. pretty sure that theta stands for the angle at which the projectile is projected. Okay. So then for the vertical, so that's the horizontal position. The vertical position is given by this equation, which you'll notice is parabolic. It's a quadratic. Now we have a new unit we haven't seen yet. Besides time and initial velocity and initial angle, we have a new unit, which is what our new variable here. H. What do you think H stands for? Initial height. So imagine that someone is throwing or projecting something off of the top of a cliff, and then it's falling down onto the ocean or something that's at a different level. So you would have to take the height of the cliff into account for your vertical location of that projectile. Does that make sense? Are you overwhelmed? Do you want me to find an example using projectile motion, or you want to just try and play around with it? I hear a no, I see a nod.